The previous video was showing some idealized support. So what we've got here is some actual supports and some actual structures, and we'll just draw on the reaction forces that you would get from these things, so from the supports and from the connecting members. And so it kind of depends on what you're thinking of as being the object that you want to do the free body diagram of. So what's the main object for you? So let's say for this one that we are actually interested in this object here. So that's the one we're trying to draw the free body diagram of. Well, and we're going to treat them all in 2 dimensions, even though they're 3-dimensional. Well, in that case, we would want to draw a force for this. It's a cable with a pin connection, and so pretty straightforward. The reaction from that is going to be in this direction. So it's a cable. It stops this moving in the direction aligned with the cable. Therefore, the reaction is in the opposite direction from that. Too easy. This one's probably on a bridge or something. It's a rocker support. And so again, we looked at that before. So we've got a smooth surface with a rotating object. And so for that one, kind of depends what the main object is. Suppose I'm interested, just move that out the way. Suppose I'm interested in this thing. That's what I'm interested in, the bridge structure that's above that. This is some kind of concrete bearing pad or something like that. Then the reaction force is going to be perpendicular to the surface because the rocker cannot push into that surface. It can't move down this way. Therefore, the reaction force must be in the opposite direction. So that's the reaction force for this one. This one here, it's a 3-dimensional problem, but you've got some beams welded together. I think these are box beams, so or are they? No, I think if I look closely, they might actually be channels, but I'm not certain. Could be a box beam. It's not actually a good thing to do to a box beam to weld it together like that. It gets a bit messy. But suppose we're thinking in 2 dimensions about the front face of this. So that's what we're interested in, and we're interested in this is what we're going to try and draw a free body diagram of. But we're going to draw it looking at this front face here. So this is a fixed connection, and so therefore you're going to have it can't move down the way, so you're going to have a reaction, can't move up the way either, but you just draw it in one direction. So it can't move that way, can't move this way either. It could draw it either way really. So there's going to be reaction in the horizontal direction as well. Could be positive, could be negative. We just draw one of them though, you don't draw both of them. And then there's going to be some kind of moment reaction as well. I usually would try and do that positive. And so anti-clockwise would be this way if I'm looking at this direction. And so for this, it's a fixed connection. It's all welded together. And therefore, you're going to have all 3 reactions, vertical, horizontal, and a moment. In reality, this might not be completely fixed, to be perfectly honest, because you've got some flexibility in all these things. But it might be a reasonable assumption to do some rough calculations. This one here, this is called a corbel. This thing here, when you set a beam on top of another little concrete element that sticks out, that's called a corbel. And probably be interested in, this would be the thing we were trying to draw the free body diagram of. And so usually we would have, well, definitely you've got a vertical reaction on that surface, to that surface. You can't push the beam into that surface. But also you'd have a friction component parallel to the surface. Depends which way the object's moving, but you just draw it in one direction. And so if it was getting hotter, this might be expanding, so it might be pushing this way. And so you'd get a reaction force in the opposite direction. Or it might be getting cooler, so it might be shrinking, so it might be moving in the opposite direction, in which case you'd get a friction component in the other direction. But when you're doing your free body diagram, you just draw it in one direction. If it comes through your calcs, you get a negative answer. The force must have been in the other direction. Okay, so that's that one. This one here, this is a pinned connection now. And so you've got some bolt pin going through there. You'd probably be interested in this object, would be what you would be drawing the free body diagram of. Pin connection, that means it can rotate. So it's free to rotate. If you cut everything off, this could just fall over by rotating around. What it can't do is move. It can't translate in any direction. And so therefore, it must have both X and Y components. And you don't draw all the other components because you could just make those up by combining X and Y components. So you're just drawing, must have an X and Y component. Okay, so it's just some real examples. There are some stuff to bear in mind here, like this really does have some friction. So there would be some friction in this pin here, and there'll be a little bit of friction for rolling even across this surface. But the reason we can just make these simplifying or idealizations or simplifying assumptions is because that friction will be so low it won't have any effect on the structure we're thinking about. Similarly for this one, yes, it might be a bit flexible, but for the simple calculation, it might be enough just to assume that's fully fixed. Again, this one here, it would have some friction in it, but the friction will be very low. And for this arrangement, I'm not exactly sure why they put a pin there. It's quite an interesting one. I can't see any reason to do that, but you'd have to see the rest of the structure to figure that out. I think that's about it. Okay, move on to the next one.